Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on probability, lecture number 13, in which I will give the concept of multiplication theorem on probability and independent events. Let us consider E and F be two events associated with a sample space S. We know that the conditional probability of the event E when the event F has already occurred is denoted by P E slash F and defined by P E slash F equal to P E intersect F by P F. P F not equal to 0. Here we may write this as P E intersect F equal to P F multiply P E slash F. This is number 1. And similarly, we may write P F slash E means conditional probability of event F when the event E has already occurred, and this equal to P F intersect E by P E. P E not equal to 0. We may write this P F intersect E means P E intersect F equal to P E multiply P F slash E. This is number 2. From 1 and 2 we see that left side is same. So we may write P E intersect F equal to P E multiply P F slash E means conditional probability of F when the event E has already occurred, and this equal to P F multiply P E slash F means conditional probability of event E when the event F has already occurred, provided that P E not equal to 0, P F not equal to 0. This is number 3. This result theory is known as multiplication rule of probability. Now we shall give an example for application of multiplication rule of probability. Example 1. A bag contains 10 black and 5 white balls. 2 balls are drawn from the bag, one after other, without replacement. What is the probability that both drawn balls are black? Means if we draw one ball from the bag, then that ball will not be returned back to the bag. This means without replacement. Now we have to find the probability that both drawn balls are black. Let E be an event such that the first ball drawn is black and F be another event that the second ball drawn is black. Now we have to find the probability that both drawn balls are black. That is, we have to find the probability of event E intersect F. There are 15 balls in which 10 are black. If we draw one ball from the bag, the probability of event E will be 10 by 15. Now that ball will not be returned back to the bag. Then total number of remaining balls will be 14 and total number of black balls will be 9. Means from 10 we have taken one black ball. So in this case we have the conditional probability. If be the event that the second ball drawn is black and the event E has already occurred, means first drawn ball is black, this event has already been occurred. So this is the case for conditional probability of event F when the event E has already been occurred. Here total number of black balls be 9 and total number of remaining balls be 14. Now this is number 1 and this is number 2. From multiplication rule of probability we know that PE intersect F means both drawn balls are black equal to PE multiply PF slash E. Here PE is 10 by 15 and PF slash E is 9 by 14, and if we simplify this we will get 3 by 7. This is the application of multiplication rule for probability. Now this case was for two events. Now we deal with the case for more than two events. If E, F, G are three events, then multiplication rule of probability will be PE intersect F intersect G equal to PE multiply PF slash E multiply PG slash E intersect F. We denote PE intersect F by PEF. Now we shall give another example for multiplication rule of probability in which we will use more than two events. Example is 3 cards are drawn successively without replacement from a pack of 52 well shuffled cards. What is the probability that first 2 cards are kings and third card drawn is an S? Now we solve this. Let E be an event such that first drawn card is a king. F be another event such that this card will be a king. But condition is that the first drawn card, which was king, was not returned back to the pack. Now G be another event such that the drawn card is an S. Condition is that first 2 drawn cards were not replaced in the pack. Now probability of event E. Since number of cards in a pack is 52 and number of kings 4, therefore probability of drawn card is king will be total king 4 by total number of cards 52. Now probability of F slash E means second drawn card is king. Condition is that first drawn card was not replaced to the pack. Means first drawn card was king, so remaining number of king will be 3 and total remaining number of cards will be 51. So this will be probability 3/51. Now we shall find probability of G, event G. Condition is that first 2 cards drawn are king and that cards are not replaced to the pack. So the probability of G under this condition, G is the drawn card is an S. Number of S's in the pack is 4 S's, but now total number of remaining cards will be 50. So the probability will be 4/50. Now we use the multiplication rule of probability for 3 events. PE intersect F intersect G equal to PE multiply PF/E multiply PG/E intersect F. And this is number 1, this is number 2, this is number 3. From 1 to 3 we get 4/52 and value of this is 3/51 and value of this is 4/50 and this will be equal to 2/5525. Now we do an experiment. Experiment is 2 coins are tossed. E be an event such that first coin shows head. F be an event such that the second coin is tail. Now, if 2 coins are tossed, then sample space S will be a set containing head head. HH means head head, head tail, tail head, tail tail. This head tail means first coin shows head, second coin shows tail. This TH means first coin shows tail, second coin shows head. And event E will be the first coin shows head. First coin shows head. This is first coin shows head. So HH, HT. F be the event such that the second coin shows tail. Here second coin shows tail, HT, and here second coin shows tail, TT. Now E intersect F is common element HT. Now we find the probability of E intersect F, E/F, F/E. Since PE, here number of elements be 2 and NS, number of elements 4, 2/4 means 1/2. PF, NF is 2, NS is 4. This is half. Here PE intersect F. Here we have one element, 1 by number of elements in sample space 4, 1/4. PE/F equal to P intersect F by PF. PE intersect F is 1/4 and PF is half, and this is half. PF/E, PF intersect E by PE. PF intersect E is 1/4 by 1/2. This is 1/2. This is number 1. This is number 2. This is number 3. this is number 4, and this is number 5. From 1 and 4 we get PE equal to PE slash F, means conditional probability of E when the event F has already occurred and both are half. Similarly, from 2 and 5 we get PF equal to PF slash E, that is half. Here we see that the conditional probability of event E when the event F has already occurred is same as probability of event E. That means conditional probability does not affect the probability of E. Similarly, here conditional probability of F when the event E has already occurred is equal to probability of F. Here also probability of F is not affected by the event E. So this type of condition shows that events E and F are independent events. This is number 6 and this is number 7. From 6 and 7 we conclude that E and F are independent events. Since PE intersect F equal to PE multiply PF slash E, and this equal to PE multiply this equal to PF. Again, PF intersect E equal to PF multiply PE slash F, and this equal to PF multiply PE. So this is 8 and 9. 8 and 9 are formulas to test that E and F are independent events. That means if P intersect F equal to PE multiply PF, then E and F are independent events. Now we prove a theorem. Theorem is prove that two events which are not impossible events cannot be independent as well as mutually exclusive at the same time. Now we prove this. Let E1 and E2 are not impossible events. That is, E1 and E2 are possible events. Possible events means E1 and E2 are not null sets. That is empty sets. E1 and E2 are not empty sets. Therefore, probability of E1 will not be equal to 0 and probability of E2 will not be equal to 0. That is, probability of E1 and probability of E2 greater than 0. If we multiply these two, then PE1 multiply PE2 greater than 0. Let this is number 1. Now, if E1 and E2 are mutually exclusive means their intersection is phi, empty set. E1 intersect E2 is phi. If we write PE1 intersect E2 equal to P phi, P phi means probability of empty set event equal to 0. This is number 2. From 1 and 2 we get that PE1 intersect E2 equal to 0, which is not equal to PE1 multiply PE2. Therefore, E1 and E2 are not independent events, because for independent events we know that PE1 intersect E2 equal to PE1 multiply PE2. Now again, let E1 and E2 are independent events. Now we consider, if E1 and E2 are independent events, then PE1 intersect E2 equal to PE1 multiply PE2. This is the condition for independent events. Let E1 and E2 are not impossible events, that is possible events. E1 and E2 are possible events. Therefore, probability of E1 greater than 0, probability of E2 greater than 0. Therefore, their multiplication is greater than 0. This is number 5. From 4 and 5. 4 and 5 here we see that in 4 PE1 intersect E2 equal to P1 multiply PE2. And here PE1 multiply PE2 greater than 0. That means PE1 intersect E2 greater than 0. Probability of an event is greater than 0. That means that event is not an empty set. So E1 intersect E2 not equal to phi. That means E1 and E2 are not mutually exclusive. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.